Okay, so we're starting to discuss rotation for AP Physics. We've just been over, we're constrained to move in a circle, so we have to have centripetal force to produce that circular motion instead of linear motion. That means we'll have radial inward acceleration. And we're just talking about the old geometry properties of a circle, like arc length and radius, and because it's physics, we're going to measure everything from the x-axis, just like always. Now, I did say radially inward, so we're going to also, we care about whether we move in and out, but let's keep it simple. Okay. All right. So in the old school system, we just had on linear x-axis, we would have our speed, our average speed is the change in distance over change in time, or calculus, say we could say, oh yeah. Let's see if I can fix this. Learn the technology. There we go. Just move that over there. Perfect. That's right. This is AP Physics. We can just say dx dt. I have instantaneous velocity if I take an instantaneous change, a derivative, and that resulted in like our old equation number one. That was v equals v0. Now there's a special time when equation one is true. Absolutely. What's the condition that I need? Sure. Okay, acceleration must be constant. If I don't have that, then I'll have like my my derivative of acceleration would not be zero, and I'd have another term and another term. Right, Peter? Okay, and I could do the antiderivative again. Okay, if I have some acceleration, then I can have like delta x equals v0t plus 1 half at squared. And that was our equation 2. And then we had equation 3. I'll scroll down in a minute. How did we get equation 3, Peter? It's the third one on the equation sheet. If I took an x integral of equation 1, no, that's a good guess though. The time wouldn't disappear. There's no time in equation 3. That was its main feature. We could actually integrate equation 3 with respect to mass and divide by 2, and that would be energy. That would be the work energy theorem. Nope. You're close. We just took equation 1, solved it for time, and substituted for time in equation 2. And then solved it around until we just had v squared. Okay, so that's really not a new equation. It's just the other two with time canceled out. Well, in radian stuff, okay, we're just going to say we have our linear velocity. Oh, this is the key. My velocity along the arc is just going to be s over t. Okay? But we're going to define this magical quantity, w, and it really is magical, it's omega, okay, as the change in theta, the change in angle in radians over time. Or it can be derivative of the angle over time. Okay? So do you remember this arc length in terms of angle and radius and speed and mass and whatever? What is the arc length if I move from here to here on the circle? And I'll give you a huge hint, and this is what you should always fall back on the test. If I went all the way around the circle once, how much arc is that? Yeah, that's 2 pi r, a circumference all the way around. How much radians is it all the way around the circle once? It's 2 pi, which is just the circumference divided by r. Okay, so the arc length is your angle in radians times the radius. Okay, that's what radians is about. It's just fractions of a circle. Every circle has a 2 pi total fraction instead of 1. Okay, because it's a circumference. It's just the fraction in terms of the radius. So my speed around the circle is really that d theta dt times r. Oh, and look. So your speed around the circle is omega r, or omega is speed over r. And that just converts it, right? If omega is v over r, oh look, okay, if omega is v over r, then acceleration oh wait, oh, okay, no, that's right. Good, good, good. If omega is v over r, then we can have, careful, that's not the angular acceleration. That's not, sorry, that's not the AC, radial inward. Just like we did before, I'll move this up. Bigger. It never wants to cooperate. There we go. Sorry. We're actually going to define our angular acceleration as the change in angular speed over time. Okay, and so if I'm just marching along the side of the circle, you could think the change in radians, say define, excuse me, oh yeah, yeah, so that the change in angular velocity, whoops, yeah, let's do it this way, make it 0 plus at, alpha t, excuse me, you have an angular speed and a change in it, maybe put delta t over there, sure, and then you'll have, I like angular displacement, because we usually start at the x-axis, but we don't have to. Alpha t, fantastic, and you can even, just like we did those, they have exactly the same form. You could substitute them. I won't make you do the substitution again. So we have all the angular quantities, where theta is just the actual distance you moved along the circle divided by the radius. This angular speed, omega, or what, is just your linear speed around the circle divided by the radius. Alpha is a little suspicious. You have to actually calculate that one. It's not centripetal acceleration. Okay. Yeah. Centripetal acceleration, if this is v and acceleration is v squared over r, centripetal acceleration is actually r times omega squared, because for each v I have to plug in omega dot r. So that's separate from those. This is not equal. to rw squared. Alpha is not equal to rw squared. Centripetal acceleration is. Okay. Let's see what else we need. We got rotational, translational. Aha. You could say, if you're accelerating along, this is AP physics, so we can grow up a bit. Instead of towards the center, if you actually move faster, you have a translational. That one equals r times alpha. And however you might calculate alpha. Yeah. Or tangential acceleration. So you have tangential and centripetal. Fantastic. We've been at that almost 15 minutes. Okay. There's one other thing I want to do before I cut my video. Let's see. All the same rules apply. Except be careful of units. Oh, you probably still needed that. Okay. So we just have radians, which is circumference, or the fraction of the circumference, divided by radius. Okay. Omega will be in radians per second. But you might also see it, and then so alpha will be in radians per second per second. You might also see revolutions per minute. Do you remember how to convert? From RPM to radians per second and back? Sure, Ben.
Divide by, well, from radians per minute. Wait, so radians per second revolutions per minute. You divide by 2 pi. Wait. Divide by 2 pi.
Okay. Yep. If I have X number of radians per second, I divide by 2 pi radians. That's one revolution. It's just a like a chemistry conversion. And 60 seconds over 1 minute. Okay. You can also take RPMs and multiply by pi over 30, or 2 pi over 60. Okay? Revolutions, because of one revolution times 2 pi, now it's in radians. Okay, 1 minute divided by 60, now it's in seconds. Okay? Any questions? Okay. Before I really lose people. Thanks, Noah. Before I really lose people, I'll let you try the first 5 or so homework problems. They're just about converting, the doing, rotation, and that stuff so far.